Howdy! Chapter 2, The Electric Field. This chapter deals with an abstract vector called the electric field. There's good news and bad news. The good news is that if you can do the problems in Chapter 1, you can easily do the problems in this chapter. The bad news is that the electric field is a strange quantity which is a vector at every point in space. Such abstract quantities are not easily understood. We do need to become very familiar with such vector fields as they play a central role in the development of the laws of electricity and magnetism. Since we are more familiar with the gravitational force than we are with Coulomb's force, let's begin by defining the gravitational field. Suppose we lived in a galaxy far, far away, and we were given the task of determining the structure of the solar system containing the Earth. Because we know Newton's law of gravity, we plan to send a probe from our planet into this solar system, record the forces that are exerted on our probe by the sun and the various planets, and using computers, calculate the positions and masses of the elements of the solar system. There's a minor flaw to our plan. All matter on our planet is antimatter that repels the normal matter that makes up the solar system. Also, everything on our planet is incredibly huge. What we think of as a small probe actually has a mass 1,000 times bigger than the mass of the sun. It will repel all the planets and the sun, blow them away so quickly that the computers will conclude that not only is there no intelligent life in our galaxy, there's nothing here at all. Clearly the probe was way too big, exerting way too big a force on the solar system. An ideal probe would be so small that it would not disturb the system it was meant to study. But if the mass of the probe is so small that the force it exerts on the planets is negligible, the force exerted on the probe by the planets will be negligible or vanishingly small. What would remain finite as the mass of the probe became infinitesimally small would be the force exerted on the probe divided by its mass. That is exactly how the gravitational field is defined. The force exerted on a probe of mass m probe by a mass m is F equals universal constant g, product of the masses over the distance squared times the unit vector, where r is the distance between the masses considered to be points, and r hat is a unit vector pointing from one mass to the other. The definition of the gravitational field produced by the mass m is the limit as mp goes to 0 of the gravitational force on mp divided by mp. What we are after is exactly the same kind of thing for the Coulomb force. We define E, the electric field vector, as the limit of the force that would be exerted on a probe called the test charge Q0 divided by the charge on the test charge as Q0 approaches 0. So, if you can find the force that would be exerted on a test charge that does not move the charges that exert the force, all you have to do is divide by the test charge and you have the electric field. It really looks more frightening than it is. We need to note one more thing. Suppose you are given an electric field produced by some charges and want to know the force a charged particle will feel. Assuming the particle does not disturb the field producing charges, all you have to do is multiply the electric field by the particle's charge. F equals QE. Summary. We defined a very sophisticated vector called the electric field E. It is a measure of the strength and positions of some distribution of charges. It is defined as a limit as some charge goes to 0, which sounds nasty. In fact, it is easy to calculate if you know Coulomb's law. You should be able to find the force that a distribution of charges will exert on a test charge Q naught. Then just dividing by Q naught gives you the vector E. You also need to know how to get F from E, and that just involves multiplication. Expect quizzes to determine whether you can do these operations. Gig 'em!